Okay, in this video we are going to look at molecular polarity. So by now you should be comfortable doing your Lewis dot diagrams. You should also hopefully be comfortable with drawing your VSEPR or three-dimensional shapes. If you're still struggling with those, you definitely want to make sure that you have those pieces kind of nailed down, because otherwise you're going to find that determining molecular polarity isn't really going to make too much sense. So to be able to determine molecular polarity, we have to look at two major factors. Okay, we have to look at the shape, but then we also have to look at the individual polarity of each bond. So if you remember back, it was either the last lesson or 2 lessons ago, I honestly can't remember, we talked about bond polarity. We talked about using the electronegativity numbers on your periodic table and how our electrons would be attracted towards whichever atom had the higher electronegativity. So when we are talking about molecular polarity, we are only concerned with what we call molecular compounds. So molecular compounds are a subset of a covalent molecule. They have only covalent bonds, but they are generally small molecules. And you'll see at the end of this video, we're going to talk about network solids, which are kind of your other type of covalent molecule. So we are going to look at the shape and we're going to look at the bond polarity, and from there we're going to be able to determine whether our molecule as a whole is polar or if our molecule as a whole is not polar. So knowing the individual bond polarity doesn't necessarily tell you what the molecular polarity is. And the reason for that is it's possible for my bond to be nonpolar but my molecule to be polar. But it's also possible for my bonds to be polar, but my molecule as a whole to be nonpolar. And that's because I have to examine the entire molecule to make that decision. So we're going to work through a bunch of different shapes because you're going to see molecular polarity definitely links to the shape that we have. So reviewing your polar bonds, right? We said we had polar bonds anytime your electronegativity was between 0.1 and 1.6, right? Remember we used those little delta plus and delta minuses, and the arrow went towards the one which had the higher electronegativity because the electron was attracted towards it. So we have to be able to recognize those pieces to help us recognize if a molecule is going to be polar or not. So let's talk shapes and molecular polarity. So if we start with the first shape, which when we went through our shapes was linear, we're going to find that there's kind of two general sets that we tend to encounter. We tend to either encounter a central atom with two non-centrals that are identical to each other, or we tend to encounter a central atom with two non-centrals that are different from each other. So what we are going to find is that when we have a central atom where both of these are the same, we're going to find that this molecule is always going to be nonpolar. Okay, even if these bonds might be polar, they're going to pull in opposite directions and they're basically going to cancel each other out, right? Think of like a tug of war. If both groups are pulling with the exact same force, the rope doesn't move, which is why we wind up with something that's nonpolar. However, if we find that we have two different non-central atoms, we're going to find that the molecule is going to be polar. So what we need to look at is basically what's the electronegativity of this one and what is the electronegativity of this one. Okay, what we're going to find is if Y is more electronegative, the general pull for electrons within the molecule is going to be towards Y. If though we find that the X is the more electronegative one, then the general pull for electrons is going to be towards the X, right? Because they have a stronger attraction for that shared pair. They're going to pull it over. It's going to wind up with that molecular polarity. So what we find is when they are not the same, this is going to be polar. Okay? The question is simply, which way does our arrow go? Does it go towards this atom or does it go towards this atom? And to make that decision, look at the electronegativity of the two. Whichever one is higher is going to be where those electrons are drawn towards. So as a general trend, you're going to find that most of the time you're looking for the atom with the higher electronegativity and that is where your electrons are going to be drawn towards, right? So our arrow indicates the direction where electrons are drawn. It's going to indicate that this side of my molecule has a partial negative charge, and this side of my molecule has a partial positive charge, because like we've talked about before, electrons have a negative charge. So if there's more electrons spending time here, this side is going to be negative. So for linear shapes, you have to look at your non-centrals. If they're all identical, it's going to be nonpolar. If they're different, it will be polar. You just have to decide which way. Next shape, we're actually going to look at bent next. So this is going to cover both possible options of either bent with one lone pair or bent with two lone pairs, right? It doesn't really matter which option we are looking at. So what we're going to find is anytime we have a molecule with a lone pair on the central atom, it is always going to be polar. So always polar due to lone pair on central atom. Okay, so my decision with bent isn't going to be, is it or is it not polar? My decision is going to be, where are electrons being drawn? So I'm going to look at the electronegativity of A, and I'm going to look at the electronegativity of the X. If the A is more electronegative, then we're going to pull up between those lone pairs, or if we only had the one lone pair, we would pull up towards that lone pair. So we're going to go up this way if the A is more electronegative than our two X's. If we find, though, that the X's are more electronegative than the A, then it's pulling this way and this way. So when we draw our arrows for molecular polarity, we only want to draw one arrow. So because both of these are pulling this way, we're going to go with what's in the middle, and we're going to pull this way. Okay, sometimes you'll see if you look up some stuff, they'll talk about like vector addition, but a lot of the times you guys haven't really done vector addition, so trying to talk about vector addition unless you've taken physics 20 and have already done it usually just leads to confusing you more. So we tend to just go with the general, it's going to pull between the two X's if those are the more electronegative atoms. Okay, if I found that these were different, like this was an X and this was a Y, then if X was more electronegative, my pull would just parallel my bond line. And if this was a Y and the Y was more electronegative, it would parallel that bond line, okay? So bent, always polar. Question is simply going to be, which way does your arrow go? Okay, next shape is trigonal planar. So we kind of have we have two options, sorry. When it comes to trigonal planar, we have the option that all of our non-centrals are the same. So if we find that all of the non-centrals are the same, because we have no lone pair, this is going to be non-polar, because again, they're all pulling with equal and opposite force, so they are going to cancel each other out. As soon as we change something though, right? So as soon as we change one of those non-centrals to be something different, this is going to be a polar molecule. The only way it wouldn't be polar is if somehow X and Y both had the same electronegativity, and there are a couple of atoms on the periodic table that do that, but it's definitely a limited number. So what you're generally going to find as soon as you change one of them is it's going to become polar. Either it's going to be polar towards Y, or it's going to be polar between the two X's. What decides which it is just which is more electronegative. So if the Y's are more electronegative than the X, our pull for electrons is going to be towards the Y. But if it's not the Y that's more electronegative, and it's actually our two X's that are more electronegative, then we are going to pull down between those two X's, okay? So again, following the same pattern of when we have non-centrals that are different, the pull is always going to be towards whichever atom is more electronegative, or if there's multiple atoms, it's going to be between those two atoms, okay? So that is what your trigonal planar is going to look like when it comes to molecular polarity. So next shape to look at is tetrahedral. So you're going to find tetrahedral works pretty similar with respect to molecular polarity as trigonal planar did. If I see that all of the non-centrals are the same, right, so these are all X, They're all going to pull with equal and opposite force, and this is going to be nonpolar. But if I find, like this option over here, that as soon as I change one of these to be something different, then it's going to become a polar molecule. The question again comes down to where is the pull? So because this is y and these are x's, kind of the same pattern that we've talked about before, if the y is the more electronegative, it's going to pull towards the single y. If the x's are the things that are more electronegative, then it's going to pull in the middle of them. And I know it's hard to think about because this is a three-dimensional shape, but if you had a pyramid, your central pull would be right smack dab down the middle. So it looks like it's kind of lining up with this x, but remember this x is a wedge, which means it's coming towards you. This molecular polarity pull is going to be just straight down in between all of those x's. Again, in class we have the model kits. It does help visualize a little bit better. But yeah, so you're going to find it's going to be polar. There's kind of a third option, and I didn't really draw it out. That third option would be if you had two y's and two x's. Then what you would want to do is recognize which is more polar. Is it the x or the y? If it was the y's, the pull would be in the middle. And if it was the x's, the pull would be in the middle of those two x's, okay? So really what you're looking for when you're looking at molecular polarity is what are the non-centrals? If they're all the same, we're looking at nonpolar. If they're different, we're looking at polar. We just have to decide in which direction it's going to be polar. The only time that wasn't true was when we had bent, because we said we had that lone pair. So the last shape to talk about is pyramidal. So you're going to find that pyramidal, just like bent, because it has a lone pair on that central atom, is always polar. Can't type polar. There we go. So the question becomes, when you're dealing with pyramidal, the same as you have with the other questions once you know that they're going to be polar, is what's more electronegative. If the A is what's more electronegative, then the pull is going to be up towards the A. If it's your X's that are more electronegative, then the pull is going to be down between all of those X's, okay? So patterns you should be recognizing. As soon as you have a lone pair on a central atom, it's always going to be polar. The question is just the direction. If you don't have a lone pair on the central atom, then what you need to look at to decide whether it's going to be polar or not is, are all your non-centrals identical? If they're all identical, it's going to be non-polar because they're all pulling with equal and opposite force, and they're going to cancel each other out. But as soon as you get one that's different, then it is going to be polar, and it's going to be polar towards whichever atom or atoms have the higher electronegativity. Okay, so this is why you have to be able to draw your three-dimensional shapes to be able to decide if it's going to be a polar molecule or not. You also have to understand how to use electronegativity numbers to decide where those electrons are going to be drawn towards. Okay, so let's do a couple of real examples so you can kind of get a feel for this. So let's look at CO2. So we've drawn CO2 quite a few times now. You should have a general idea that this is a linear molecule with those two double bonds, right? And if you have to go about drawing the dot diagram to figure that out, then that's okay too. You can definitely spend the time to do that, right? Remember, we only show lone pairs on the central atom. We don't show them on the non-centrals. So this guy has a linear shape because we had two electron groups and no lone pairs. So now to decide whether it's going to be polar or not, I look at my non-centrals. Okay, no lone pairs, so that doesn't automatically make it polar. These are both O's. Because they're the same, they're going to have the same pull. So this is going to be non-polar. But now let's look at SO2. So if we were to draw out SO2, right, we would have the same general setup of an O, then an S, and then another O. But if we count out how many valence electrons we're actually allowed to have, we're allowed to have 18. right? So if we were to think about it, we would say 18. We'd say we have 3 atoms that all want 8. So 24 for a full valence. That gives me a difference of 6, which means 3 bonds. So 1, 2, we're going to have to put a double bond in to make this work, right? So we get to 3 bonds. Now we have to fill our valence shell. So this O only has 2, so 4, 6, 8. Sulfur has 2, 4, 6, so we need to give it a pair. And this O has 4, so 6 and 8. So from my dot diagram, I need to decide what shape this is going to be. So I have 2 things attached and 1 lone pair. When that happens, that means we have a bent shape. So we have our S with its lone pair. We have our double bond to our O. And then we have our other O hanging out down here. Right? And we don't need to show the lone pairs on these ones because they are not central atoms. So when we look at this, this is for sure going to be polar. And we know it's going to be polar because it's the bent shape with the lone pair on the central atom. And like I said earlier, anytime you have a lone pair on the central, it's always going to be polar. The question is, should it go up from the S or should it go down between the 2 O's? To make that decision, we have to look at the electronegativity of S and O. Whichever one is higher is where it's going to be drawn towards. So when we look at our periodic table and we look at those electronegativity numbers, it's the O that is going to be higher, which means the pull for electrons is going to be this way. Okay, so I don't have to write the word polar because my arrow indicates that it's polar and it shows me where it's going. The only time I need to write words is if it's non-polar, because then I don't put any arrows in. So I need to make sure that it's clear that I recognize it's non-polar and that I didn't just forget to draw an arrow. Okay, so if it's non-polar, write the word non-polar. If it is polar, you're going to include your arrow in whichever direction the pull for electrons is going to be. Okay, so at the start of this lesson, I talked about how we have covalent molecules. Okay, and in Science 10, we always just are like, oh, covalent molecules, right? And so covalent molecules basically means that we are sharing electrons. So when we get into bonding, we see that we can actually divide covalent molecules into 2 categories. Okay, we can divide them into moleculars, and we can divide them into network solids. So in both cases, when we're dealing with moleculars and network solids, we are still sharing electrons. The difference generally comes down to how many atoms are involved. If you think about a molecular, right, think about water, it's the most common molecular that you're most familiar with. It's only H2O. It's got a pretty small formula. One of the differences you're going to find between moleculars and networks is that network solids have huge formulas. And that's because they consist of sometimes millions of atoms all covalently bound together. So why we distinguish them, even though they both consist of covalent bonds, has to do with when we start doing phase changes. So if you think about taking ice and melting it into water or boiling water and turning it into water vapor, it still stays water all the time. The water part of it doesn't go away. We're breaking attractions between one water molecule to the next water molecule. Whereas in a network solid, so kind of classic example of a network solid is a diamond. If I wanted to melt a diamond, I have to actually start breaking covalent bonds. So that's where you're going to see that big difference. And in maybe the next lesson, potentially the one after, can't remember, we are going to talk about phase changes and how much energy is involved. And you're going to see that's where differentiating between moleculars and network solids really comes into play. Okay? So when we are talking network solids, these are solids in which dozens, even millions of atoms, often the same element, sometimes not the same, are bonded covalently into continuous 2- and 3-dimensional arrays. So for our purposes, in Chem 20, we are concerned with 3 network solids. we are concerned with carbon. We are concerned with SiC, so silicon carbide, and we are concerned with SiO2. Okay, so we have carbon, glass, and sand. Okay, these are all considered to be network solids. You need to make sure that if you see one of these three formulas, you recognize that that is a network solid, because it's going to behave differently than a molecular, even though they both share the fact that they have covalent bonds in common between them. So if we're talking about carbon, don't draw this picture. Obviously, it's printed in your notes for you. But these are kind of 4 different possible ways in which we can create network solids with carbons. So they all have very different physical properties associated with them. So this first image here, A, this is graphite. So anytime you're using a graphite pencil, you're basically shearing off a layer of carbon. So if you think about carbon, we've talked about how carbon has 4 valence electrons, so it wants to make 4 bonds. You can see by looking at this image that we have this trigonal planar shape going on. That's going to account for 3 bonds. Where the 4th bond comes, it's this kind of weak attraction between one layer and the next. So when you're writing with a graphite pencil, you're basically shearing off a layer of carbon as you go, because these bonds are pretty weak. And so you're kind of cutting it off here, and you're leaving this layer on your sheet of paper. Okay, then this, we change the shape now. It's now all covalently bound in a tetrahedral shape. This is diamond. Diamond is one of the strongest, hardest substance known to man. And that's because of the way it's all bound together. It's all very tightly locked into place. It takes a lot of energy to be able to break that. Okay, then we have these guys over here. This is buckyballs. So again, it's still all going to be carbon atoms. There's usually around 60 of them in it. Kind of looks a little bit like a soccer ball if you think about the way the shape is. So these are kind of, I don't want to say they're not hypothetical. They are a real thing, but they're looking at how to use them in medicine, being able to put something kind of on the inside of the ball and maybe be able to deliver it specifically to certain locations in the body. And then here we have our nanotubes, right? So they're basically long tubes. What you find is we go back to that trigonal planar orientation, which accounts for 3 bonds. And where the 4th bond comes from is a double bond that kind of hops all around. So because that double bond hops all around, we have electrons that are constantly moving, which is why nanotubes have the ability to conduct electricity. Okay, so be familiar with your 3 network solids, because as we start talking about melting point and boiling point, that is going to definitely come into play. You also need to make sure that you are comfortable recognizing molecular polarity, because that is also going to come into play when we start looking at analyzing intermolecular versus intramolecular forces.